Hello you all. This video is a part of Laboratory in Physics 1 course. In this video, we are going to study the experiment number 9, which is about the coefficient of expansion of metals. Let's begin with the objective of this experiment. There are main three objectives. The first one is to study linear expansion of solids. Second, to investigate the relationship between change in length due to thermal expansion and an overall length of metals. And the last one is to determine the linear expansion coefficient of brass, iron, copper, and aluminum. To give you some background, let's talk about how metals change when they are heated or the thermal expansion. When a matter absorbs a thermal energy or heat, such energy leads to an atomic vibration throughout the matter, where each atom is assumed to be connected via an ideal elastic spring, like shown in the left figure. The higher temperature the matter has, the faster atomic vibration will become. So let's check out this figure. You can see the system at different temperature. The left hand side is at low temperature. Even at very low temperature, atom in the system still vibrating. But what different when you increasing the temperature? You can see each atom in the system will vibrate stronger, and it take more volume for each atom to vibrate. So what you can see here is this increasing temperature will result in the volume expansion of the material. So the volume expansion. And if the vibration is too strong for a spring to hold an atom together inside the material is going to change its phase. Like when water is heated, it becomes steam, right? However, in this experiment, we will only consider the change in solid, where there is no phase transition. The atomic vibration in materials are different due to several factors like the composition, atomic ratio, the way that each atom is interconnected to form a structure. So each material is going to behave differently under thermal expansion. So we can see how important if we understand the material property under thermal expansion. For example, it can give a good guideline when one wants to select a material that's suitable for a certain application and to optimize material design, especially for those that are likely to operate it under high temperature. And if we do not understand about the material property, the material may undergo some adverse effect of thermal expansion, like what's shown in the following figure. This one is a concrete cracking, and you may have seen this in your real life before, and railway bending like this. So these two unfortunate situations can be prevented more or less by just dividing the long length of material into shorter segments and adding a small gap between each segment as shown in this figure, which we call expansion joint. And this can give some space for the material when it gets heated to expand itself. Anyway, to describe the nature of thermal expansion, there is one physical quantity that we should know about. It is the coefficient of linear expansion. Basically, the thermal expansion occurs in all dimensions of matter. To make it easier for us, in this experiment, we will only study the expansion in all dimensions. This is called a linear expansion coefficient, which is here denoted by alpha symbol. This quantity describes how the size of an object changes with a change in temperature, as given in this equation. Or we can simply express this equation in the form of delta L like this, where delta L is an extended length of material at a certain temperature T, and this is the temperature that we want to change to, or we can say the final temperature of a metal tube. L naught is an initial length of the material at T naught, where we consider T naught as room temperature in this experiment. Room temperature. And delta T is the change in temperature of metal tube from room temperature to T temperature. And this one would be 100 degrees Celsius as we go into flow hot water steam into metal tube. So we assume that the temperature of metal tube should be as close as 100 degrees Celsius. And in the picture, you can see an increase in length of ceramics and metal when they are both heated to the same temperature. And clearly, metal has longer extended length, as you can see here. And this suggests that a metal has a higher linear expansion coefficient if compared with the ceramics. Okay, now let's move to the equipments and experimental setup for this experiment. And in this figure, you can see the equipment that we need and how we set up them. So let's talk about the first one, which is very important. It is the metal tube. And there are 4 types of metal we consider in this experiment as shown here. The first one is aluminum, brass, copper, and iron. And you can notice that what difference between them when we observing it is the color. So we can use the color to differentiate them. And they are all made in the tube shape. And this is because we're going to flow some hot water steam to adjust the temperature of the metal to observe the thermal expansion. As we need to flow the water steam inside this tube. So that means we have to boil water as well. And that's why we also need electric stove that connect to the circuit breaker, and this is for safety reasons. And next one, we also need a small bowl. And this is because the hot steam will come out in this direction right here. Come out like this. And then hot steam will condense. So in that case, we need some container to store this hot water. And next, which is very important, we need coefficient of expansion apparatus, because this will be used to fix metal at a certain initial length and also to fix another important equipment in this experiment, which is a dial gauge micrometer, which is required to measure an extension of length of metal tubes. And during the experiment, we have to touch the metal when we want to remove and change from one metal tube to another. So in this case, we need a piece of fabric so that we can hold the metal and the rubber tube and remove them. And the last but not least, we also need a cooling bath, which may not appear in the figure, to help reducing the temperature of metal tubes to room temperature faster. Okay, so next, let's talk about a dial gauge micrometer. Even though you may know how to read the value from a dial gauge, so let me go over those procedures one more time. A dial gauge consists of 2 types of scales. The first one is main scale, as you can see here. It's located near the center. And the other type of scale is dial scale, which is fixed with the outer frame. This one, the outer one, and this one is connected to the outer frame. So we can rotate this scale according to this longer pointer. Each division on the main scale, this one, is equivalent to 1 millimeter, and this equivalent to 100 division on the dial scale, this one. So that means if this long pointer rotate for one turn, the short pointer here will move from 0 to 1, and another turn, then it moves to 2, like this one. And from this, we can find the resolution of the dial gauge. Okay, 1 division on main scale equal to 1 millimeter. So the resolution would be 1 millimeter divided by 100 division. And this 100 division is the division on the dial scale. So that means the resolution of this measuring tool is 0.01 millimeter per division. Okay, so let's practice a bit in this figure. So try reading the value, how much you would get. Here, we start from the main scale, right? And you can see here that the short pointer is point around 1 to 2, right? So that means we get 1 millimeter from the main scale. And from the dial scale, you see that the long pointer is here is 2 division, right? Around 2, but it's not exactly 2. So I would say 1 point something, 1.2. Okay, this could be 1.2 division on the dial scale. Each division is equivalent to 0.1 millimeter. So that means it would be 0. How much? 0.22, right? Millimeter. So that means the total length that read from the dial gauge is 1.022 millimeter. Okay, and there are 3 decimal digits there. Okay, so this is important. Okay, I almost forget to mention that when you want to set 0 for this micrometer, you can rotate the outer frame, and this outer frame is fixed with graduation plate. Okay, then you can just rotate until the 0 mark on the dial scale point exactly on the long pointer. And now we come to the last part of this video, which is about procedure. In this experiment, there are 2 parts. The first one is the measurement of thermal expansion. First, we read and record the room temperature as T0, and then fill water into the pot. Only half full is enough. As you can see in the video, fill the water, only half full is enough, because when it's boiling, the water is boiling, it may spit out of the pot. And then just close the pot with a cover. And you can notice that this cover had something that you can fix with the base of the stove to make sure that this pot is not going to move during the experiment. Next, tighten the clamp to the base of coefficient of expansion apparatus at 200 millimeters. So there are 3 lengths that we use in this experiment: 200, 400, and 600. And we're going to start from 200 millimeter. And you can see that this is the clamp that we use to fix the initial length of the metal tube, which you can move from 200 to 400 or 600. And then place the aluminum tube on the base into the guide fitting, which is also attached with the clamp. I will show you in the video later. Next, tighten the tube to the clamp and then connect the steam outlet of the pot and the aluminum tube by a rubber tube. You can check from this picture. On the metal tube, there are link grooves as well, and this is the groove that indicate the length of the metal at 200, 400 and 600 millimeter. And we have to connect the metal tube with a rubber tube like shown in the figure, so that water stream can flow through the metal tube. And when you do experiment, do not insert the rubber tube too deep, as it is not only hard to remove but also very hard to hold when you want to change the metal tube. Okay, this is the video, and what I'm showing is the ring groove on metal tube, and here this is aluminum tube. Okay, then you insert the aluminum tube into the gliding fitting attached to the clamp like this one, and make sure that the ring groove is placed exactly at the clamp as shown here. It should be like this, not like this. Okay, after the metal tube was fixed on the base, we also need to do the same for dial gauge that is used to measure the extended length of the tube. To be able to measure the length correctly, make sure that the gauge is firmly fixed and the end of the tube and the gauge head are met, like in this figure. And then rotate the out frame of the gauge to adjust its long pointer at 0, like this one. This is to set 0 for the dial gauge micrometer. Okay, and in this figure, it shows this is the screw that we use to tighten the dial gauge. Then turn on the circuit breaker. In this step, we will observe the change in length of metal tube. So we have to wait a little bit until the pointer of dial gauge stops moving. Then read and record the value of extended length in the report. And next, after there is no change in the length of the metal tube, turn off the breaker and remove the rubber tube from the steam inlet of aluminum tube. At that moment, the rubber and metal tube is hot, so we need a piece of fabric. And then take out the metal tube and leave it in the cool water bath for about 3 to 5 minutes until the temperature of metal tube reduced to the room temperature. Then you change from aluminum tube to another type of metal and do the same from step 4 to 9, and then change from copper to brass, then do the same from step 4 to 9 and change from brass to iron tube. And after you complete all types of metal tube, change the position of the clamp from 200 mm to 400 mm as shown in the video. Okay, you complete 4 metal tube, then you remove this clamp from 200 mm and you use this screw like this, and then you put it at 400 mm mark like this. And after you change this, you replace the step 4 to 10. So that means you have to start again from aluminum and then do the same and change from aluminum to copper, then from copper to brass and then to iron. After that, you repeat those process again, but change the position from 400 to 600 mm mark. And that's all for the experiment. Then you plot a graph between the extended length delta L and initial length L0, and then find the slope for each data set of the metal tube. And the second part is about calculation of linear expansion coefficients. So in this part, first you approximate the change in temperature of the tube, and to approximate this we use the boiling temperature of water, which is 100 degrees Celsius, with respect to the room temperature, where we assume this is the temperature T of the metal tube. Okay, then you get the delta T. Second, determine the coefficient of linear expansion for each metal tube using linear regression method, okay, from this equation. And if you compare with the linear equation like this, then you know the slope of the plot is alpha times delta t, right? And we already know delta t from the first step in this part. That means you can find alpha, right, which is the linear expansion coefficient. And the last step is compare the obtained coefficient with the standard. Okay, should be standard. The standard value and calculate their percentage errors. And that's all for this experiment number 9. Okay, thank you for watching.